one thing is for sure that we are going to find some edges. And you know that what is segmentation? Segmentation is dividing the whole object or the whole scene into different regions. And you must know that, and you must remember that whenever you are moving from one region into the other region, you are traversing an edge. For example, whenever you are moving from one country to the other country, or one city to the other city, or from one locality to the other locality, you are traversing an edge. And as soon as you traverse an edge, you know that you have entered from one region into the other region. So these edges, they will define that how many regions are there and what are the boundaries of those regions and how you can separate out those regions. So edge-based segmentations, they rely on edges. Okay, so to find an edge, we can use different edge detecting operators, which you must have studied. What are the edges? Edges are the discontinuities in gray levels. And whenever you are moving from one region into the other region, gray level is going to change. So if you can find that discontinuity, you can find the edge. That edge detecting operators, they cannot directly give you a segmented output. They will provide you edges, they can detect edges, but you have to do something else to find a segmentation output. Okay, so supplementary processing steps must follow to combine edges into edge chains so that all edges are combined, and they will produce borders of the regions, and then later on region growing or region-based segmentations or region filling operations, they can be used to fill the regions so that you can get a whole segmented output. So in edge-based segmentation, the aim is to reach at least a partial segment, at least something on which we can apply region-based segmentations or region growing processes to get the segmentation output. So we need some partial segmentation. We never aim to find a completely segmented output using edge-based segmentation techniques. The most common problem with segmentation-based methods is that the presence of an edge where there is no edge, because an edge detector can easily give you a false information. And the other thing, where there is an edge, the edge detector might not detect it because of its direction or because of some other problems. Okay, so these are the most common problems, because if you miss an edge, you will miss a region. For example, if this is the output of an edge-based detector and you want to segment out this object using edge-based segmentation technique, and this is the output of some edge detector. Now you can see that there is a problem over here. So now when you'll apply, for example, region growing over here or region filling, what is going to happen? For example, you start from here, you start filling this region, you keep on filling, you keep on filling, you'll meet the edges, you won't fill beyond this thing, you won't fill over here. So when you'll come over here, you will leak out, and now this whole image will become the part of the object. So it's like a hole in a beaker. So if you keep on pouring water, the water will keep on going out from that hole. So now this whole region will be filled and you will not be able to find this single object present over here. If we look on the type of the edges, because if we want to find all kinds of edges, we must know that what are different types of edges present. So we have a simple step type, we have a simple step ramp, we have a smooth ramp over here. So it is a smooth ramp. You can see the edges are quite smooth. This one is a simple ramp or a continuous ramp because the gray levels keep on changing. This one is like a ridge, and this one is an impulse. So if you know all kind of edges, now if you find these kind of discontinuities in gray levels, then you know that there is an edge over here. You must have studied some edge operators that are used to detect edges in the images. One thing which I should mention over here is that a simple edge operator or an edge detector, it will give you readily the magnitude of the edge. But there is something else associated with an edge. For example, you are standing at the end of a cliff. You are standing somewhere over here. And for example, there is a river over here and you are standing over. You know the magnitude of the edge, so you won't try to jump over it, but you want to move along the edge. So in order to move along the edge, you must know the direction of the edge as well. This direction information is going to help us in later analysis of edge-based segmentation techniques. So direction and magnitude both are necessary over here. Okay, so some edge detectors, they are designed to give you both pieces of information, that is the magnitude and the direction. Whereas there are certain other edge detectors that will only give you the magnitude, but direction information will be hidden somewhere in that. So we will see both of them. For example, a simple modification of already known X and Y direction gradient mask, they can be used to establish direction information, and I'll explain this point after I guess 1 or 2 slides at how we can use them. And sometimes there are certain edge detectors which are called template matching edge detectors. These edge detectors will give you the magnitude and the direction in one step. So what are these things? You can picture them as multiple edge detectors. For example, one edge detector is expert at detecting horizontal edges only. Another similar kind of detector is expert at detecting an edge at 45 degrees direction. Another, for example, edge detector, it is expert at detecting vertical edges. So you have an edge detector for this kind of edge. For this direction of edge, this is the 45 degree, a vertical direction, and this one. So you have a 0-degree edge detector, a 45-degree edge detector, a 90-degree edge detector, a 135-degree edge detector. And what these edge detectors will do, they will all give you magnitude of the edges which they are detecting. For example, you apply these 4 edge detectors at a certain location, and these 4 edge detectors are giving you, for example, this one is giving you a 5, this one is giving you, for example, a 9, this one is giving you a 20, and this one is giving you, for example, an 8. So you can easily see that all these edge detectors, they are detecting some edges, but this edge detector is giving you the highest magnitude. So this will be the magnitude of the edge, and this will be the direction of the edge. So these template matching edge detectors, they can be used like this to find the magnitude and the direction of the edge in a single step. So these are certain masks template matching edge operators that can give you the edge magnitude and direction as well. So over here only two direction edge operators are given, but you can go through the reference text for other direction edge operators. Okay, and I hope you can easily figure out that what a 90-degree pre-width mask would look like. You just need to rotate it. What if you are going to use one edge detector only, one or two edge detector only, and not all other edge masks? What was the problem? What is the problem with the template matching edge operators? The problem is that you cannot figure out precisely the direction of the edge. It can only give you, for example, if you are using 4 edge operators, template matching edge operator, one for 0 degree and 45 degree, 90 degree and 135 degree, then you have to convince yourself that the edge present is either a 0, a 45, or a 90, or a 135. For example, there might be an edge at 70 degrees. You cannot find it. You have to assign it a 45 or a 90. So to tackle this kind of problem, we can use two edge detectors only, one for 0 and one for 90 degrees, that is the horizontal and a vertical edge detector, and then mathematically figure out the direction information. So we can use any edge operator. For example, you can use a Sobel edge operator, you can use a Kirsch edge operator, you can use a Prewitt edge operator, and you know that one will give you a horizontal edge magnitude, the other version of it will give you the vertical magnitude of the edge, and you can agree on the combined on the total magnitude by using any of the formulations. For example, you can find the overall magnitude like this, or like this. So there are different ways to agree upon the magnitude. And now if you know the direction, if you know the magnitude in x direction and in the y direction, then what would be the net direction of the edge? But there is only one way to figure that out, and that is using arctan function, inverse of tan. So tan direction y divided by direction of x, that is the magnitude in y direction. This is the magnitude in y, and this one is the magnitude in x. So you can use these two magnitudes, use an arctan function, and figure out the direction of the line. Now this direction can be anywhere between 0 to 180. So you don't need to worry that what about a 70 degree or a 85 degree direction. So this method can give you all the directions between 0 to 180. Okay. So here are certain edge operators that can be used for this kind of detection. So for example, if we talk about Sobel operator, this one will give you x direction edge, this one will give you a y direction edge. And to figure out the combined direction, you can use the arctan function. One thing is for sure that whenever you apply edge detector on an image, ideally there should be 0 everywhere and there should be non-zero values at the location of edges. But things are not ideal. In fact, they are never ideal. So you are not going to get a 0 value anywhere. You are going to get some small values corresponding to some non-significant gray level changes. So they can be resulting from quantization noise, small gray level differences, or anything else. So you can apply simple thresholding to remove all small changes, and you will be left with edge data only. Okay. For example, this one is the original grayscale image. So this is the original grayscale image. If you apply an edge detector on it, this will be the output of the edge detection. And now if you apply the onto this edge detection, if you apply thresholding, this is what you are going to get. So you can see that in place of a significant edge, you are getting a black line, and everywhere else you are getting a white line, white area. And then you can use region filling or some region growing methods to convert this edge image into a segmented image. You can see that it is not a very good output. But there are certain other things associated with edge-based segmentation which we are going to study. So one problem is that edge detectors, they normally produce thick edges because as the gray level is smoothly changing, the edge detector will keep on producing high non-zero values. And instead of a very thin, for example, like this edge, you are going to get a thick edge. So how you can convert this thing back into this one? So there is a very easy method for that. You can use some form of non-maximal suppression. For example, you can see all these pixels, you can visit all these pixels, and if you know the direction of the edge, that is this direction, see in the direction which is perpendicular to direction of the edge, and all the pixels present in this direction, keep only the maximum of it. Let me explain it like this. Let me draw another thing. For example, so let me draw an edge like this. You have, for example, some 10 value over here, 5 value over here, 10 over here, 5 over here, then 10 over here, 5 over here, 5 over here, 10 over here, for example, like this. Now you know that this is the direction of the edge. A non-maximal suppression would work like this, that you, when you are, for example, standing over here in this location, you will see in this direction that is perpendicular to the direction of the edge. And in this direction, whatever pixels you are seeing, you are going to keep the pixel having maximum value of the edge. So you will be left with this pixel only. So when you are over here, you will be looking in this direction. So you will be left with this pixel only. So at the end, you are going to get an almost thin edge with one, which will be 1 pixel thin. Okay, I would like to recommend you guys to go to the text and see and study about this non-maximal suppression in a bit more detail. So this will be the result of a non-maximal suppression technique. So you can see that over here there are thick edges, and these thick edges will be converted into thin edges. So after that, it is quite probable that such data will still be cluttered by noise. There will be some portions, some edges, which you cannot say that whether these are correct edges or wrong edges or false edges. So how we can eliminate those things? Now, there are certain pixels which are having non-zero values, but they might not be the part of an edge. How to decide that whether this non-zero valued pixel is part of an edge or not? So we are going to use another modification of thresholding called hysteresis thresholding to provide a solution for this problem. So supposing that edge magnitudes exceeding T1 can be taken as certain edge, and all the pixels having magnitudes less than T0, they are not edges. So what about pixels which are having values between T1 and T0? This hysteresis thresholding is focusing on these pixels. That is, the pixels having values between T1 and T0. So what is going to happen? We are going to mark all the pixels which are having magnitudes greater than T1 as correct. That is, they are part of an edge. So this is the first step. Secondly, we are going to remove all the pixels that are having magnitudes less than T0. Okay, so now in the image we will be left with two things. A pixel having a value greater than T1, we know that that is an edge. A pixel having a value between T0 and T1. Now what to do about these pixels? Now we will look onto the pixels having values between T0 and T1 only, and we will see that if that pixel is in the neighborhood of an already marked pixel, then we will say that, okay, this pixel is also an edge pixel. But if there is no edge pixel already present in the neighborhood of this this pixel which we are analyzing, then we won't mark it as an edge pixel. Okay, so I can illustrate this thing through this diagram. So what is going to happen? For example, this is T1, this is T1, and this is T0. So all pixels which are having value less than T0, we know that these are not edge pixels. So we can remove them. All pixels which are having value greater than T1, we know that these are edge pixels. So we are certain that these pixels are edge pixels. Now what about these pixels? This portion C and this portion B. So we are going to come over here. We are going to analyze this pixel. We are going to see that there is one neighboring pixel that is already marked as an edge. So we'll mark this pixel as an edge as well. Now we will move forward. We will come to this pixel. And once again, this pixel has an already marked edge pixel, this one. We will mark this pixel as an edge as well. And in a similar fashion, we will keep on moving, and we will label all these pixels as edge pixels. But what is going to happen over here? When we are going to start from this point, there is no neighboring pixel that is already an edge. So this portion will be regarded as a non-edge portion and it will be deleted. So it will not be an edge. So it will be deleted. Okay. So this hysteresis thresholding, what it has done, it has contained or it has sustained all the edges which have values greater than a certain threshold, that is T1, and it has successfully retained all these edges which failed to have value greater than T1, but still they were part of an edge. So this hysteresis thresholding retained these values and it removed these false edges. So this will be the result of hysteresis thresholding. You can see that all non-zero pixels which were present over here, all non-zero pixels present over here or over here, where they have been removed because these non-zero pixels were not part of the edge. These were not the edge pixels. So now you can use uh, any region growing technique to grow a region over here, and you can easily get a fully segmented portion. Okay, so that's all for this lecture. And these are some references which I would recommend that you guys should go through.